Hello. In this video, we're going to look at proofs. Proofs are going to make up a large portion of the calculus course. We're going to be proving many of the things we look at. So we need to understand what a proof is, what it isn't, and why we need to do proofs in general. So to start, what is a proof? Well, the closest thing you've seen to a proof in pre-calculus is a trig identity. If someone gives you, for example, cotan x plus tan x equals secant x cosecant x, this is an identity that apparently is true, and you can prove it. What you're asked to do in a trig identity is to show that these two sides are equal to each other, which is a type of proof. Generally, the structure is as follows. You start with the left-hand side of the trig identity. Then you use logic, algebra, trig definitions, and you work it and you work it and you work it, and eventually you've been able to transform the left-hand side into the right-hand side. And then at the bottom you put left-hand side equals right-hand side, and you've completed your proof. Now, we need to ask the question of why should we prove something. For example, couldn't we just do the following? Let's take x equal to pi by 4 and look at our trig identity. Well, cotan of pi by 4 is 1, tan of pi by 4 is 1, 1 plus 1 is 2. Secant of pi by 4 will be 1 over cosine, so it'll be, instead of root 2 over 2, it'll be 2 over root 2. And then cosecant, again, will be 2 over root 2. 2 times 2 is 4, and root 2 times root 2 is 2. So this gives us 4 over 2, which is just 2. Okay, 2 equals 2. We plugged in on x value that we had, and it appears that the left-hand side equals the right-hand side. Isn't this enough? Isn't taking x equal to a particular value and showing that you get the same thing on both sides, isn't that enough to prove the identity? Well, the answer, of course, is no. This is not a proof, this is a specific value. And the reason why this isn't a proof is the identity is supposed to be true for every single value of x, and you've only checked one particular value of x, so you haven't proven it for all x values. Now, let's take a look at a bit of a different problem. How many regions do you count in this circle? So, we've got 1, 2. All right. Let's go ahead and add another point and then connect the lines. How many regions do you count now? Well, 1, 2, 3, 4. All right, so we're going to add another point, and then we're going to connect the dots and count the regions. Take a guess at how many regions you're going to have when you add another point. All right, 1, 2, 3, 4, 5, 6, 7, 8. Was that what you guessed? Did you assume there was going to be 8 regions? Maybe, maybe not. What do you think is going to happen when we add another point? Go ahead and take a guess at how many regions you're going to get when we add another point. Well, it's looking a little crazy here, but we can count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and of course, 16. Hopefully you're starting to see a bit of a pattern. We've got 16 regions here. So, we have the following. We could summarize this in a little table. When you have 2 points on the edge of the circle, right, this example here is just, here's your circle, here's your 2 points, and you draw a line, you get 2 regions. When you add a third point, you get 4 regions. When you add a fourth point, then you get 8 regions, and so on and so forth. So the question would be, since we've drawn it for 2, 3, 4, and 5, we've got 2, 4, 8, 16, how many regions would you have when you do 6 points? So you make 6 points along that circle, and you count the number of regions. So go ahead and take a guess. How many regions are you going to get? Well, here's the diagram. It's pretty crazy, and I encourage you to pause the video and go ahead and try to count up all the regions. See how many there are. Well, hopefully you gave it a good try, and maybe you came up with a number, maybe you didn't. We're going to go ahead and look at all the regions, and I've numbered them to help us see how many there are. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31? That can't be right. Well, look at the diagram. Did I double count anything? Did I miss anything? No, it looks like I've got it all. Apparently there's only 31 regions, not the 32 that you were probably predicting. Well, and that's actually pretty obvious if you look at the table. This is your classic sequence of numbers. It's the 2, 4, 8, 16, 31, 57, 99. Surely you've heard of this pattern before, right? 2, 4, 8, 16, 31, 57, 99? Oh, yeah, because you were thinking it was the squares, right? You were thinking it was going to be 32 and then 64 and then 128. No, it's not the squares. It's this pattern. And if you're wondering where this pattern comes from, you can actually see it on Pascal's triangle. What you do is you draw Pascal's triangle, and then you go ahead and look at the rows. So the first row here gives you 2. This row gives you 4. This row gives you 8. This row gives you 16. Now the next row would give you, of course, 32. But you don't add the whole row. You only add up to the first 5 entries in the row, which gives you 31. And if you check the next row, 1 plus 6 plus 15 plus 20 plus 15, that's going to give you 57. And then, of course, the next one will be right here, which will give you 99. Now, this is important because you were likely suspecting that the pattern was 2, 4, 8, 16, 32, and so on. And if you did that, and you had assumed that, and you hadn't actually drawn the last one, you would have come to an incorrect conclusion. Because the pattern of, oh, it's just powers of 2, it seemed like that was likely. We had done a few examples, and we began to believe it was true, but we had not given a proof. And so without a proof, all we're doing is taking an educated guess. It might be right that that's the pattern, but in this case, it turned out to be very, very wrong. And this should caution you that you need to be careful. If you don't have a proof for something, you might be just jumping to a wild speculation. Now, if you were going to prove this formula, this is the following formula. It's n to the power of 4 minus 6n cubed plus 23n squared minus 18n plus 24 over 24. It's not just 2 to the power of n like you thought it was going to be. Now, again, I still haven't actually proved that this formula is true. You can go ahead and look up a proof for this on the internet if you're wondering where this formula comes from and how the formula is actually proved. But this is actually the formula for it. It's not just powers of 2. It's quite a complicated formula, either visualized on Pascal's triangle or visualized with this formula. So like I was mentioning, the takeaway is that just because something appears to be true doesn't make it so. You need an argument. You need some type of proof. And so proofs, they're very, very, very important in mathematics. Without a proof, all you have is a guess. And your guess might be right, but hopefully you've seen in this case that your guess can be very, very wrong. The beginning pieces of information may lead you astray, and so you need proofs to guarantee that things are true. But of course, not all proofs are made equal, and we're going to look here at a very interesting proof, or proof in air quotes. So we're going to suppose A is equal to B. Then I'm going to multiply this equation by A. So I'm going to multiply by A and A. That's going to give me A squared equals AB. Now I'm going to subtract B squared from both sides. Well, if I subtract B squared from both sides, it looks like I've got some factoring I can do. Here I have a difference of squares, so I can factor that, and here there's a B in common, so I can factor that. So I'll get A plus B, A minus B, equals B, and then A minus B. Well, notice we've got an A minus B on both sides, so we can cancel that, giving me A plus B equals B. Now, if you remember, at the top we assumed that A was equal to B. So instead of writing A plus B, I can just write the A as a B, because A and B are the same thing. So this will be B plus B. Well, of course, B plus B we know is 2B. And finally, I can divide both sides by B, giving me 2 equals 1. Now, wait a minute. Wait, 2 equals 1. That doesn't seem reasonable. That doesn't seem logical. Hopefully you learned in school that 1 plus 1 is 2, and 1 is not the same thing as 2, right? If you've got one thing, that's not the same thing as 2 things. But apparently I just proved that 1 thing and 2 things are the same thing. That doesn't really seem reasonable. But can you find a flaw in my argument? Can you find an error in the proof? Go ahead and pause the video and See if you can find my mistake. Is there a mistake? Is this true? Surely it can't be true because 1's not 2, but where's my mistake in my logic? All right, I'll end the suspense for you. The mistake is right here in these two steps. When I go ahead and cancel out the a minus b, what I'm actually doing is I'm actually dividing by a minus b. I'm dividing both sides by a minus b and dividing by a minus b so I can cancel it out. But if I divide both sides, if I divide by a minus b, a and b are actually equal to each other. So what I'm doing is I'm technically dividing by a minus b, which is equal to 0. Because a and b are the same thing, so when you subtract them, you get 0. Well, I'm dividing by 0, and hopefully you know from your math education that you can't divide by 0. Dividing by 0 is illegal. It's inappropriate. It's breaking a basic math rule, a fundamental rule of mathematics. You're not allowed to divide by 0. So, of course, this proof is incorrect because I'm dividing by 0, and when you divide by 0, in fact, this is why you're not allowed to. If you were allowed to divide by 0, then the rest of this proof would be technically correct, and you would show that 2 equals 1. But of course, 2 does not equal 1, and so that's one of the reasons we forbid dividing by 0, because it would mess up all of our math. It doesn't make any sense. And so you have to watch out that when you're proving something, you don't accidentally break a math rule. You follow all of the rules you know to be true. Otherwise, you could prove very strange things. And so proofs are not just random scribbles of algebra. They have to be logical, and they have to follow the basic math rules. Now let's look at an example proof, the quadratic formula. This is a very famous formula. Hopefully you learned it in grade 11. If you have a quadratic like this, the solutions are given as negative b plus or minus the square root of b squared minus 4ac over 2a. But where does that come from? Where is that formula derived from? How do you know it's true? Did you see a proof? Maybe you saw a few examples, but how do you know it works on every polynomial? You would need an ironclad proof, and that's just what I'm going to give you. So we're going to start with our polynomial ax squared plus bx plus c. And what we're going to do at the very beginning is we're going to multiply both sides by 4a. And you'll see why that's useful in a minute, but just trust me right now, this is what happens often in proofs, is there's a step or an insight that initially seems a little strange, but it's very useful in the end. And so for right now, go ahead and take my word for it that multiplying by 4a is a good idea. Well, when we do that, 4a times 0 is just going to give me 0. And on the left-hand side, I'm going to go ahead and distribute. So we'll get 4a squared x squared plus 4abx plus 4ac equals 0. Now next up, I'm going to move the 4ac to the other side. So 4a squared x squared plus 4abx equals negative 4ac. And I'm going to use the skill of completing the square here. Roughly what I need to do is go ahead and get this thing to become a perfect square. And what I need for this is actually b squared. So I have 4a squared x squared plus 4abx plus b squared. And if I add it to one side, of course, I have to add it to the other side. Now, let's look here. This makes our factoring wonderful on the left-hand side. It will factor down as 2ax plus b times 2ax plus b. If you're not quite sure how that factoring works, you can go ahead and expand to check it. b times b will give me my b squared. 2ax times 2ax will give me my 4a squared x squared, and the middle term 4abx will come from the 2axb and the 2axb. So that's definitely a correct factoring. And since we have two of them, we can go ahead and square it up. Well, the next step would be to solve, because we're trying to get x by itself. We want to figure out what x equals, so let's square root both sides. 2ax plus b equals plus or minus the square root of b squared minus 4ac. Maybe you're starting to see the formula come together a little bit here. Next up, I've got to move that b to the other side because I want x all by itself. So I'm going to get negative b plus or minus the square root of b squared minus 4ac. And finally, I want to divide by 2a to get x all by itself. minus b plus or minus the square root of b squared minus 4ac over 2a. Well, there you go. We finished our proof. And usually when you finish a proof in mathematics, you put a little box at the end. It signifies that you finished the proof. Sometimes you'll put QED, which in Latin is standing for that which was to be demonstrated. It's just a formality in mathematics that tells the person reading your math that you've finished your proof. So there you go. We have our proof. We've shown that the quadratic formula is true. And again, initially, this proof might be a little bit complex to understand. There's some strange factoring, but if you follow the steps, you'll see that at no point did I divide by 0. At no point did I break any math rules. And it starts to make sense of where this formula comes from. There's a little bit of trickery involved where I multiply by 4a at the beginning. But as soon as you get that step down, you realize that, oh, I'm just trying to isolate for x, I'm trying to complete the square, and the rest of it sort of falls apart naturally, and you get your solution for the quadratic formula. So hopefully you enjoyed this video on proofs. We're going to be doing a number of proofs in the calculus course to ensure that everything that we talk about is actually true, that you're not just taking my word for it or your other teacher's word for it or the internet's word for it, but that you actually understand that there's a logical argument for why we're allowed to do the things we do. So I hope you enjoyed this video, and as always, thanks for watching.